We're doing Calculus, Chapter 5, Section 3, the Fundamental Theorem of Calculus. I'm your host, Dr. D. Okay, here we go. The Fundamental Theorem of Calculus. Another name for this, the Fundamental Theorem of getting a 5 on the AP exam. It is seriously important and you need to learn it. Okay. Fundamental theorem has two parts. Part 1 says if you have a function that's continuous on the closed interval a to b, and you have another function that's the integral of that function. Okay, so g of x is the integral from a to x of f of t dt, where a is your, well, basically a is any constant. Then g prime of x equals f of x. What does that mean? That means if I take the derivative of this integral, I get the original function. The derivative of the integral is the original function. So basically what you could say is that differentiation and integration are inverses of each other. Now that's not technically correct, but this is really technically what it says. If I take the derivative of the integral, I get my original function back. Now we're going to go over some details of that in some of the example problems that you need to understand, but this is the statement of fundamental theorem part 1. Now, part 2. If f is continuous on closed interval ab again, then the integral from a to b of f of x dx equals capital F of b minus capital F of a, where f is the antiderivative of small f. In other words, the derivative of capital F equals small f. So in other words, what we're doing here is to evaluate a definite integral. Then all you're going to do is take the antiderivative, plug in b, take the antiderivative, plug in a, subtract the two. So to find the area under a curve, the shortcut to doing those tremendously long Riemann sums is just plugging in a and b to the antiderivative. So that's a huge shortcut. So let's try some stuff here. So g of x is the integral from 0 to x of the square root of 1 plus t squared dt. G prime of x. Now, fundamental theorem says that if I want the derivative of this whole thing, all I do... Oh, no, it's in blue. How embarrassing. All I do is put in the x value into t squared. And that's it, game over. Now the 0 doesn't matter. It could be any constant. So in other words, if I had g of x equals the integral from negative 5 to x of the square root of 1 plus t squared dt. Now g prime of x equals 1 plus x squared. So notice the lower limit of integration doesn't matter as long as it's a constant. So that's it. Now let's try another example. Same idea. We've got the integral from 0 to x of sine pi t squared over 2 dt. Now s prime of t is just going to be sine of pi x squared over 2. That's it. Game over. Okay, now, here's another notation for doing the same thing we were just doing. I could rewrite this and say g of x equals the integral from 1 to x to the 4th of secant t dt. And then say find g prime of t. And that's going to equal secant. Now I'm going to put my x to the 4th in there for t. Now, there's one other complication here. If the upper limit of integration is a function, then you have the chain rule. See, if this was just x, then I put x in, I'd be done, just like the first two examples. But since it's not just x, it's a function of x, then I have to multiply by 4x cubed. So, that's basically what we're doing here. Let's just go back. Notice, like I said, if I give you g of x is this, and I say find g prime, well, that's the same thing as saying, okay, I want the derivative of the integral. So the derivative of the integral is secant of x to the 4th, and then we have to multiply by the 4x cubed. So do not forget to multiply by the derivative of the upper limit if it's not just a single variable. Now, oops, gotta take two. Yeah, let's do this. Now, just to make it a little more clear, didn't get that. Just to make it a little more clear what the answer is, I'd rather go 4x cubed times secant of x to the 4th as my final answer. Just so I know it's the secant is only of the x to the 4th and not the 4x cubed. Okay, so another one. G of x is the integral from this function to 5 of natural log t dt. Now, first thing, the constant needs to be on the bottom. It can't be on the top. So what we need to do is we need to say g of x equals the negative integral See, I need the lower limit of integration on the bottom. So, instead of going from 3x squared plus 2x minus 1 to 5, I'm going from 5 to 3x squared minus, or plus 2x minus 1. And so I need to put a negative out in front anytime I flip the limits of integration. Because if I'm going from 1 to 3, that would be backwards of going from 3 to 1. And I would have to change the sign. Okay, so that's the first thing we have to do. Constant on the bottom, variables on the top, have to change the sign. Now, g prime of x is going to equal natural log, oops, forgot the negative, negative natural log of 3x squared plus 2x minus 1. Now, don't forget the upper limit was a function, not a single variable. So we need to multiply by the derivative, which would be 6x plus 2. So the final solution then would be negative 6x plus 2 times natural log of 3x squared plus 2x, oops, plus 2x minus 1. Okay, so remember, if you need the constant on the bottom, you need to flip it to get it there. Okay, now let's do one more that's related to this. Okay, if I want dx of, oops, all right, so those kids outside were quieter when I first got started. Okay, now, notice I don't have a constant on the bottom. So I can't just plug in the variable into the function. So what I need to do is I need to break this up into two separate integrals. So this is going to equal the derivative of the integral from x to anything, any constant, let's just make it 0, of sine t dt, plus the derivative of the integral from 0 to x squared of sine t dt. Notice what I did here. Instead of going x to x squared, I'm just going x to 0 and then 0 to x squared. Now, the only thing you have to keep in mind is both of these have to be constants, and I like just making them 0. It makes it simpler. So now, once again, we want constant on the bottom, variable on the top. So I need to flip this one. So I make this the derivative of the negative integral from 0 to x of sine t dt plus derivative from 0 to x squared of sine t dt. All right, now I'm ready to apply the fundamental theorem part 1, and that is plug in x for t. So this is just going to equal negative sine x. Now, plus sine of x squared. Now, notice I plugged in my x squared. It's not a variable, it's a function. So I need to multiply by the derivative of the upper limit, which is 2x. So I'm going to clean this up now and say, put the 2x in front, so 2x sine of x squared minus sine of x. That would be the final answer. So remember, if you have variables on the bottom and top limits, or the lower and upper limits, then you need to split it up into two separate integrals. So it's from x to 0, and then from 0 to x squared. And remember, integrals are sums. So I can break up any integral into two separate sums, and then add them up. Okay. E to the x, the integral from 1 to 3 of e to the x dx. Now this is an area under a curve. So basically we're using fundamental theorem part 2 here. So the antiderivative of e to the x is e to the x. So I just go, it's e to the x from 1 to 3. And what this symbol means is I plug in the 3, and I plug in the 1, and I subtract the 2. And so that's basically what we have, is e cubed minus e. That would be a number, so that's my final answer. All right, now, we've got a parabola here. We want the area under that parabola. So if, yeah, let's just look at what that looks like. Yeah, we'll pull out our Desmo. Let's see here. Rats, I put it away. Okay. All right. Let's see, what did I... Negative x squared minus 4x plus 8. Negative x squared minus 4x plus 8. Ooh, this is going to have some negatives in it. All right, this is a decent one to do. We want the integral of this. Now, you know, let's just simplify this. Yeah. Nah, still not enough. Okay, now we got it. All right, negative x squared minus 4x plus 16. What we're doing is, well, let's just do it right here. Okay, so f of x equals negative x squared minus 4x plus 16. And we want the area between x equals 0 and x equals 2. So basically what we're doing is we're getting the area under this curve from 0 to 2. That's the area we're getting. All right, so the integral from 0 to 2 of negative x squared minus 4x plus 16 dx. So don't forget your dx here. Now this equals the antiderivative. So that means we go negative x squared becomes negative x cubed over 3 minus 4x squared over 2 plus 16x from 0 to 2. So this equals, let's just go negative 1/3 x cubed minus 2x squared plus 16x from 0 to 2. Now when I put a 2 in here, I have negative 1/3 times 8, which is negative 8/3, minus 2 times 2 squared, which is minus 8, plus 16 times 2, which is 32. And now when I put zeros in here, I have 0 minus 0 plus 0, which is 0. So basically this is the area under the curve right here. And that is, well, let's just go negative 8/3 minus 24 thirds plus 96 thirds. And that's 96 minus 32 is 64 thirds. 64 thirds. Or what's that turn out to be? 21 and a third. Well, let's see if that makes sense. This area here, from 0 to 2, let's get rid of this. It's kind of obscuring things. Okay, if I were to count the squares here, notice, see, that actually looks a little low. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. No, it could be right. 12, 13, oh wait, 12. Yeah, 12, 13, 14, 15. Yeah, if you count the partials in here, yeah, that's going to be like 21 and a third. That definitely makes sense. So notice all we did was we took the antiderivative, we plugged in 2, we plugged in 0, we subtracted. And that gives us the area under the curve. Fundamental theorem, part 2, shortcut. Okay, now, all right, so just a few more. The integral from 3 to 6 of dx over x. Okay, this really equals the integral from 3 to 6 of 1 over x dx. Now, what's the antiderivative of 1 over x? Well, you can't just say it's, see, this would be the integral from 3 to 6 of x to the negative 1 dx. So you can't just go, oh, okay, raise it by 1, so it'd be x to the 0 over 0. Can't do that. So what is the integral of 1 over x, or the antiderivative of 1 over x? That is natural log x. So this becomes natural log x from 3 to 6. So that means we have natural log of 6 minus natural log of 3. And if you remember your properties of natural log, this just becomes natural log of 6 over 3, which equals natural log 2, which that's my final answer. Okay, now, find the area under the curve, the cosine curve from 0 to pi over 2. What's cosine curve look like? Looks like this. Now, we only care about the area from 0 to pi over 2. So that's the area we're looking for right there. Okay, how do we get that? That's just going to be the integral from 0 to pi over 2 of cosine x dx. What's the antiderivative of cosine x, or the integral of cosine x, is sine x from 0 to pi over 2. And so this equals sine of pi over 2 minus sine of 0. And sine of pi over 2 is 1. Sine of 0 is 0. So we just found out that area equals 1. That's kind of handy. Okay. You know, let's just do one more thing. What if we want the area from 0 to pi over 2? Okay, so I want that area now. I'm not 0 to pi over 2, 0 to pi. See, this would be pi right here. So I want the area from 0 to pi. Okay, well, let's do the same thing. So we're going from 0 to pi of cosine x dx. So that's going to be sine x from 0 to pi. That's sine of pi minus sine of 0. Sine of pi is 0. Sine of 0 is 0. Why is that area 0? Okay, it's 0 because that's a positive 1, that's a negative 1. Notice if I wanted the area from pi over 2 to pi, watch this. See, if I'm going from, yeah, I didn't need to change that. Okay, so I'm going to go, I want the area from pi over 2 to pi, which is going to be sine x from pi over 2 to pi. So that means I've got sine of pi minus sine of pi over 2. Now what's sine of pi? That's going to be 0. Sine of pi over 2 is 1. So the area from pi over 2 to pi is negative 1. So what we just found out is this area is 1. This area is negative 1. And when I add it up, I get 0. From 0 to pi would just be 0 because they cancel each other out. Okay. All right, one more delicious example problem. That is the integral from negative 1 to 3 of 1 over x squared dx. Okay, so I should be able to do the integral from negative 1 to 3 of x to the negative 2 dx. Okay, so what do I do then? Is I raise the exponent by 1 and divide by that value. So then I put in a negative 3. Well, let's clean this up a little. X negative 1 over negative 1 is really going to be negative 1 over x from negative 1 to 3. And that means I'm going to have put a 3 in there. That makes negative 1/3 minus, and put a negative 1 in there. So negative 1 over negative 1, which would be minus 1. And that would be negative 4/3. That can't possibly be right. Watch what happened. Yeah, we're going to go back to our graph. Okay, so we have 1 over x squared Nope. Come on. Why is this not working? All right, let's try it like this. Okay, that's it. There's 1 over x squared. Now, I wanted the... Yeah, we'll just go back to this. Okay. So notice I was looking for the area from negative 1 to 3. So from negative 1 to 3. And I ended up with a negative. Why is that? Okay, the reason is because this function is not continuous from negative 1 to 3. There's a point of discontinuity. Notice if I have y equals 1 over x squared, and I'm trying to go from negative 1 to 3, then I'm going across an undefined value. And if we go back to our original statement, wrong direction. If I go back to my original statement, fundamental theorem part 2, if f is continuous on a to b, then the integral is going to be the area under the curve. Our function was not continuous on a to b. So you need to be careful that if you see that in between your two limits of integration is a discontinuity, or even if one of the limits of integration is discontinuous, then you can't just cruise right on ahead with your antiderivative and get the area, or else hackage will ensue. Okay, that's it. Have fun with these.